Good morning, everyone, and welcome to the BEST tutorial track. I'm Lee Lacey from SOAR Technology. I'm a member of the tutorial board and the chair of the BEST tutorial committee. And I'll be the chair of the session all day today. In the back, we have Dr. Ramona Shires from Aptima. She's going to be helping out this morning. One of the things she's going to be helping with is the feedback forms. We would really appreciate your help in filling out the feedback forms so that we can improve the conference each year. It's also available online through the app if you'd prefer to do it that way. Several announcements for you. As a courtesy to our presenters, please double check to make sure your phone is either off or silenced. Each tutorial is 80 minutes long, and there's going to be 10 minutes for Q&A at the end, so please hold your questions until then. If you need to leave the presentation before it's over, please use the back doors and not the side doors. There's no flash photography or video recording, but feel free to take non-obstructive photos, stills during the session, and feel free to share on social media. As a reminder, all the conference registrants are eligible to obtain CEU credits for papers and tutorials, so if you weren't scanned when you came in, please make sure you get scanned. And this afternoon, after the tutorials, we've got the ITSEC Fellows presentation. That'll be at 4 o'clock in room 330 ABCD, and that'll be Dr. Wink Bennett presenting. There's only a 45-minute break between this tutorial and the last one, so lunch is kind of tight. If you've got an exhibitor badge, there's some food options on the show floor. If you don't, there's some food vendors that are going to be set up on the second floor lobby area. So the second tutorial of the three is also one of the three nominated for Best Tutorial. Of the 33 tutorials this year at ITSEC, the three in this track were selected as candidates for the Best Tutorial Award, which will be announced at the banquet on Thursday night. So the second one is number 21, An Introduction to Cognitive Systems for Modeling and Simulation. And it's by Randy Jones, and co-author was Dr. Dylan Schmoro. Dr. Randy Jones is the leading developer of knowledge-rich intelligent agent software at SOAR Technology. He's been a principal investigator for a variety of advanced R&D projects funded by ONR, ARI, DIMSO, DARPA, and other DoD agencies. He has previously held teaching and research positions at Colby College, the University of Michigan, University of Pittsburgh, and Carnegie Mellon. His areas of research include computational models of human learning and problem solving, executable psychological models, and full-spectrum intelligent behavior models. He earned a BS in math and comp sci at UCLA, and MS in 87 and PhD in 89 degrees from the Department of Information and Computer Science at the University of California, Irvine. His co-author in the front row is Dr. Dylan Schmoro. He's been an integral contributor to the field of cognitive systems for modeling and simulation since the late 1990s. As a government funder at the turn of the century, Dr. Schmoro played a pivotal role in supporting early advancements in this domain, collaborating with SOAR Technology even prior to joining the company, following his distinguished career in the U.S. Navy. Dr. Schmoro continues to champion the development and application of innovative cognitive systems. While he's not presenting today, he remains deeply passionate about the topic and is here to support Dr. Randy Jones in sharing their joint insights. So please join me in welcoming Dr. Randy Jones.
Thank you. Good morning, and thanks for coming. I want to start by asking how many of you feel like you use some form of automation in your personal or work life? All right, good. And how many of you feel like that automation, whatever it is, makes your life or your work easier than, say, 20 years ago? Okay, now how many of you are using automation that's so productive that you now have enough time to do everything you want? No, okay. All right, so what I want to focus this tutorial on is one particular form of automation where there's still a lot of potential yet to be realized, which is cognitive systems. So what we are calling cognitive systems is a particular, say, subfield of artificial intelligence where we are simulating how people think. There's a lot of philosophical argument about whether there really is a simulation of thinking. Maybe a simulation of thinking is just thinking, but we're not going to get into that here. But our objectives for this tutorial is to describe what I mean by cognitive systems, to examine some of the benefits and distinguishing features that set cognitive systems apart from other types of automation and software systems, to compare the programming style and engineering style of cognitive systems versus other types of systems, to explain a concept called least commitment, which we feel is central to how cognitive systems work and approach the way they automate decision-making. We're going to give a couple of supporting examples to try to ground the conversation, make it more relatable, review some decision-making you can use to decide, well, if I have a problem that I want to automate, is cognitive systems the kind of automation I need for that, or can I use something else? We are going to give you sort of a rubric for making that type of decision. And then this is a new learning objective for this tutorial. When I gave this tutorial 10 years ago, machine learning existed, but it wasn't exploded like it is now, and I didn't really have to talk about it. But now I do. So we will talk about the relationship between cognitive systems, how people think, and the explosion in learning systems, how machines and people learn. So why are we talking about cognitive systems? And this gets back to my questions about automation. If we want to assure deterrence through integrated training and readiness, we have to raise the bar of what we can currently automate. We want to use automation as a cognitive multiplier. So this, at this conference, we focus on training and education, so we can focus on making instructors more effective. We can focus on making training simulations more effective. But obviously, we think cognitive systems go beyond training, simulation, and education too. The basic idea is that a cognitive system can do some of the thinking for you. Now, most automated systems are force multipliers, but they're not necessarily cognitive multipliers, right? They can automate rote tasks. So they can automate some simple forms of decision making, but in general, they're not thinking about your goals. They don't even have a way for you to tell them what your goals are so they can help you achieve those goals, and that's where cognitive systems come in. They bring in judgment and situational awareness to our tools, and they're able to anticipate and exploit the cognitive constraints and tendencies of adversaries. So cognitive systems aren't just things that help us, they help us build models of the people we're working with or the people we're working against. And a big part of cognitive systems is we feel that they're a necessary part of building collaborative teams. Collaborative teams, you need to be able to interoperate with your automated system the way you interoperate with your human teammates, right? You need to have a shared language, a shared understanding, shared goals, and you need to trust each other. Cognitive systems provide the infrastructure for allowing you to build these types of systems. So if we sum this all up, there's a bunch of different kinds of automation that cognitive systems can provide, and it's all focused around sense-making, judging, making decisions, basically all the things we lump together that we call thinking when a human is doing it. And the point I want to emphasize here, that we're going to distinguish cognitive systems from other types of software systems or automation, is that cognitive systems have a why in them. They are not just doing what they're told, they know why they are doing what they're told, and that allows them to think about how to do what they're being asked to do. So what are some of the benefits of human-like cognition that we want to focus on in detail so we can engineer them? So cognitive systems, the best example we have is a human. We make quick decisions. We make good decisions quickly, especially experts, right? One feature of humans is that there is such a thing as an expert, right? There are novices and there are experts, and the experts can make better decisions than the novices, and they can make those decisions in general more quickly than the novices. They are able to generate emergent behaviors that are purposeful and adaptive. And what I mean there is we have goals. We have goals we want to achieve, and we figured out we figure out ways to synthesize our knowledge so that solutions to achieving those goals emerge, and we can adapt those approaches as the situation changes. The best experts at tasks are really good at changing what they're doing when the situation changes, understanding how things have changed and understanding what do I need to do differently now if I still want to achieve my goals. This involves reconsidering my interpretation of what's going on. Maybe changing what my goals should be, changing what my plans are to achieve those goals. One of the examples I use as an expert, it's getting kind of dated now, but Wayne Gretzky, as a hockey player, one of the things that was always said made him one of the best hockey players ever was he always knew where everybody was on the ice. I mean, obviously, he's only looking in one direction at a time, but he somehow knew where everybody was. He had that situation understanding, and he knew what his goal was, right? To pass or score the goal himself. And because he knew where everybody was, he could instantly change and adapt his plans to achieving those goals. That's the kind of automation we want to think about being able to provide in a cognitive system. If we compare this with, say, what we'd call traditional artificial intelligence. Now, I'm not talking about generative AI here yet, but I'll talk about it next because that's what's out there. Traditional artificial intelligence is more the kind of expert systems and decision-making systems that have been built in the past that didn't necessarily really try to mimic how humans do it, but we're just trying to be functional. You know, give me a problem and I will search for the absolute best solution for that problem. These systems were computation intensive. You know, they would take a long time to find the best solution to a problem. Traditional expert systems from the 70s and 80s would do this kind of thing where they would maybe have rules or search mechanisms for taking in a goal and trying to consider all the different ways you might achieve that goal. There were also reactive systems with no internal state, and I would say that the best familiar example to this might have been the Roomba you have in your house, but the Roomba from 10 years ago, okay? If you have a Roomba now, it builds a map of your house, and it can be smart. It uses smart approaches to make sure that it's covering the rooms you want it to cover and that it's vacuuming all the spots. 10 years ago, the Roomba just went in random directions. It didn't have a map. It just figured, statistically, I'm going to get everywhere eventually, right? That's a reactive system with no state. It was able to avoid trying to go under the couch. It was able to avoid going off the stairs, but that was about it. It didn't have really goals, in a sense. It was just behaving and not understanding why it was doing what it was doing. Modern machine learning, now we get into the generative AI, is also computation intensive. So where I'm contrasting this with cognitive systems, humans are, we're slow compared to computers, but we're really good pattern matchers. We can very quickly assess a situation if we're an expert, and we can very quickly map that situation into a reasonable, maybe not the best, but a reasonably good solution to achieving our goals. Machine learning systems are very computation intensive. If you go and interact with ChatGPT or Copilot online, it's really impressive what it can do, but it takes some time to think about what it's doing. If you were relying on that, say, to fly a combat aircraft, that might not be fast enough, right? You don't want to wait 10 seconds for it to generate a plan for what you should be doing. There are still these so machine learning systems really, for the most part, are still reactive systems with no internal state. As capable as these large language models are, they don't really build a representation of an internal representation of what are we talking about here, right? They take in the entire conversation you've had with them as input, but that's all, in a sense, external input. It's not building this internal representation of, oh, here's what I'm talking about. And that's why you can play with it. You can do things like say, whatever answer it gives you, you can say, oh, that answer was wrong. It could have been right. It could have been wrong. It will believe you, right? It will say, oh, I'm sorry. I got the wrong answer. Let me give you a different answer. And then you can say, well, that answer was wrong too. And it'll say, oh, I'm sorry. Let me give you the first answer again then. Because it doesn't have this internal model of, why am I answering these questions? It's just answering the questions, right? The machine learning systems are purely statistical. So there's a question. Maybe humans are purely statistical too, right? But at least what I'm calling cognitive systems aren't purely statistical. They have what we call symbolic reasoning. So we reason about concepts. We reason symbolically, especially when we're doing symbolic things like mathematics or chemistry, or we're even adding numbers or multiplying numbers. That's manipulating symbols. Machine learning algorithms are currently not that great at that because it's all statistics, and because of the statistics, they often get close to doing things right, but they often don't get things quite right. They get things statistically pretty good, which is very useful for lots of things, right? But not for what we're talking about with cognitive systems. So what makes cognitive system software different from other types of software we use for automation, for training, for simulation, for education? So one of the big things is these systems need to have knowledge. Okay, if we're doing symbolic reasoning, we have to have some encoding of the expertise that sets experts apart from novices. But, presumably when we're building cognitive systems, what we're usually interested in is building expert-level cognitive systems. Not always. Sometimes we want to build, an accurate model of a human, whether or not they're an expert. But either way, humans have knowledge, and we are trying to simulate that knowledge. They have significant breadths of behavior. They don't have just individual things they're really good at, right? So a smart thermostat is not a cognitive system. Even though it's the best thermostat out there, it can handle all sorts of different changes and smartly managing your electricity for heating your home. It doesn't have breadth of behavior, so we don't call it a cognitive system. Cognitive systems are able to be interrupted, and they don't forget what they were doing, just like humans, right? We can switch tasks. We can walk and chew gum at the same time. If your partner asks you to do something else, you go do it, and then you go back to what you were doing. You don't forget what you were doing, and you're opportunistic. If you can do two things at once or kill two birds with one stone, you can figure out how to do that, and you do that. Lots of automated systems are not capable of doing that kind of thing. We can adapt when the environment changes, right? So this is just being, again, situation understanding, always knowing what's going on when the situation changes. I'm able to make smart choices to react to those changes. Other things we're not going to talk about so much in this tutorial are emotional and social factors. Obviously, that's a big part of human cognition. There has been research on how that can be incorporated into computer models of cognition, but that is still fairly young research. Learning, well, we're going to talk about learning, but most of this talk will not be about learning. We're talking about a different form of AI here, and then we'll relate it to learning. And then the least commitment reasoning I mentioned before, and I'm going to give a detailed example of that so you know really what I'm talking about when I talk about least commitment reasoning. Basic idea is that a cognitive system has an explicit representation of its situational understanding. So it is encoding internally, internal representations of the justifications behind what it's doing. That's another way of saying it has a representation of why it's doing what it's doing. This also happens to lead to traceable and inspectable decision-making, because if the system knows why it's doing what it's doing, it can communicate that to you, hopefully, right? You can ask it, why did you do that? And it will tell you. So this allows us to, this is just one piece of cognitive systems. We can train as we fight. If we want, for example, to have training simulations with realistic opponents, those realistic opponents better be cognitive systems. If they're not human role players, we want to be cost effective, we want to build automated role players. They need to think the way the humans do, or we're not training as we're fighting. And that means that those synthetic opponents we're training against understand why they're doing what they're doing, because they're going to be reacting to what we're doing, and they're going to be trying to achieve their own goals, and they're going to be changing how they achieve those goals based on what's going on in the situation. So before we get into other meat of it, I want to talk about a little bit about, well, how do we build these cognitive systems? What's the approach? And part of the issue here is, I would argue there's no such thing as a complete intelligent system, right? You can always make a person smarter by teaching them more, right? And you can always make a cognitive system smarter by giving it some more knowledge or enhancing its capabilities somehow. So if you're engineering cognitive systems, what do you do? We're not gonna just build the perfect cognitive system, because possibly there is no such thing, right? And even if there were, it's gonna we've been working on AI for 70 years now. We haven't built it yet, right? So what do we do? If we're working on building a cognitive system for a particular application, we first focus, like any software system, on the requirements. Okay, what are the cognitive requirements for this application? So for example, I need you to build me some synthetic combat pilots that act like Russians. Use Russian tactics, for example. So you have to scope the problem. So you start with the requirements, but as someone who's been building these systems for decades, I can tell you the kinds of requirements you get from the customer are not really usually very helpful. It's like, well, you're building me an intelligent system, right? So it should just always be smart. I don't know how to tell you what's smart and what's not, but just make sure the system always does the smart thing. Okay, that's not that actionable as a requirement for building software, right? And then I've actually had this happen. I was building a system that was to train air traffic controllers on aircraft carriers. So I was building the pilot who would land on the aircraft carrier and interact with the air traffic controller, and we got it working. It was landing. It was beautiful. And then the customer said, okay, but since we're training people, I need it to make mistakes sometimes too. Okay, well, and it should make the same mistakes that real human pilots make. And I'm like, I wish you had told me that when we started, because I spent all this time just making it do the task correctly. But okay, that's a reasonable requirement. We need to make sure we make the same mistakes people do. That can't be the only requirement. I have literally seen AI research papers that argued this must be an accurate model of human cognition because it does the same dumb things that humans do. Well, okay, that's only part of what we need the cognitive systems to do, right? We want it to do all the good things humans do too. For a training, it shouldn't be predictable or boring, right? Because then the trainee gets bored and doesn't train well. There's always room for more intelligence. So we need good requirements. We need to know, how is it that a Russian pilot actually makes decisions and implements their tactics? What are the goals they're trying to achieve? How do they achieve them? How do they work together? The best way we've found so far is to do that in a scenario-driven way. We work with human experts. So expert combat pilots, experts on Russian air tactics, whatever. We get experts, we give them scenarios, we say, all right, tell me how this would play out. What would you do at each time step on here? What alternatives would you have considered, and why? I always need to know why. Why did you do this? Why didn't you do this other thing? What did you consider, and why did you reject it? All these things go into the design of the cognitive system. Then we apply these decision-making principles. We figure out what kind of language do the experts use to think about the problem that they're solving or the mission that they're performing. How do they talk about the way they understand the different kinds of situations they can be in? How do they talk about the different kinds of goals they're trying to achieve? Because usually there's more than one goal. Sure, there's the mission objective, but there's also staying alive, there's managing your weapons, there's all sorts of goals, and they interact with each other. And the more they interact, the smarter you have to be to make good decisions. So we get all the information we can about how do these human experts represent the tasks they're working on. And we refine that decision-making into an actual formal language. Then we decide, okay, we can't do everything, so where do you want to start? Which parts of this decision-making do you need to be good for now? And then we'll expand it once we've got that done. We prototype and test, and then we iterate. And we can do this forever. So like I said, you can always make an intelligent system smarter. So we just keep going through this loop. Okay, we've got air-to-air intercepts going really well. Do you want to do air-to-ground now? Okay, let's iterate. We can share some of that knowledge, and we can reuse some of the things we used in air-to-air. Some of it will be new. We add new representations. We add new decision-making principles. And we keep going until we have what we want. Like with any really large software system, it will probably never be finished, but we can keep making it better and better. Now, in the tradition of this conference and training, simulation, and education, the software approach that has largely been used to build what I would want to use cognitive systems for has been what they call finite state machines. Okay? Finite state machines are a software approach where you define these things called states and say, as long as you're in this state, here are the kinds of things you should be doing. And then if something happens out in the world that might change the state you're in, and then there's a different set of things you should be doing. And you go from state to state until you finish your mission. This is an attractive approach for several reasons, which I'll get into. They apply a rigid context for plans. So you're either in a state or you're in some other state. And while you're in this state, you do the things that are relevant to that state. This allows you some limited kind of contextual action. So like with Wayne Gretzky, we might imagine he's in different states at different times, and he's in a state where he's considering passing the puck, he's in a state where he's considering taking the shot. Okay, so there's some context there. That's what these states provide, and humans are great context-based reasoners. So this is an attractive approach. They allow us to use procedural programming, which is, by far the dominant paradigm in software engineering, writing procedures that call each other. So within each state, we can have just your normal everyday software engineer write the code of here's what's supposed to happen inside this state. That makes the approach cost-effective. It makes it long-lived because I can write my state programs in C or C++ or Java, and in 10 years, after I've gone to some other job, someone else can take that over and they can keep extending the code. So all the stuff in there is convenient and familiar, and that's really attractive from a cost-effectiveness perspective. Okay, but there are some trade-offs. So if you're using finite state machines, they're very familiar to software engineers. That's a good thing. They give you an efficient implementation. So finite state machines can run very quickly enough to manage, say, a simulation of an air-to-air engagement, right? Even a supersonic aircraft, making decisions at that pace. And they're done in traditional computer languages, so that's a plus. But there's a number of things that are not that great about state machines. So they give us a traditional linear flow of control. You're in one state, you go to another state, you go into another state. In each state, you're executing procedures. This is, in a sense, the opposite of of this idea of I'm always making the best decision quickly at the best time. As the situation changes, if I'm locked into a state, I can't be as sensitive to changes in the world as I might like to be. I'll give you examples to explain that further. It's difficult to handle task switching, interruption, and opportunism. So these things I talked about previously that humans are really good at, doing two things at once, switching from one task to another and then back, taking advantage of opportunities like, again, I'm going to use this air combat example a lot. If a threat pops up on your radar, an expert knows what to do. If I was already heading in that direction anyway, I'm going to do something about this threat popping up the radar. I can take advantage of an opportunity to kill two birds with one stone, for example. Achieve my mission goals, but also achieve something else that popped up. In a finite state machine approach, that's very difficult to do because you're in this state, and if something happens that's relevant to some other state, there's a question, well, do I jump to that state, or do I keep doing what I was doing, or do I somehow merge the two states together? You can do that, but the more you do that, the less you're really using finite state machines, and you're just making things more complex, and you're losing the advantages of state machines. There's not really a fixed way to represent situational awareness in finite state machines. So you will have, in each state, you'll have some variables holding information. You'll probably have some global variables holding information that's relevant to lots of states, although that, in a sense, violates the whole idea of finite state machines. It's all ad hoc. These systems don't really know why they're doing what they're doing, except to say, well, I'm in this state, and this is what I've been told I'm supposed to be doing when I'm in this state. Right? There are other data structures that contribute to that decision making, but again, it's all ad hoc, and so I list that as a trade-off. The main thing here is that the organizational assumptions and strengths will not scale with complexity, and I will talk about complexity in a bit. The finite state machine idea is attractive in a sense because it's simple. It's simple, it's a simple approach, it's simple for even junior software engineers to wrap their heads around, but when you get into these complex situations where you're reasoning about multiple goals, doing multiple things at the same time, trying to be smart and understand the situation, you are less and less taking advantages of the strength of the finite state machine, and more you're complicating things. In addition, learning capabilities, there's no obvious integrated way to integrate learning into these finite state machines. There are some obvious ways, but they're simple. They're very low level. So the take-home message here is that the simplifying constructs that make finite state machines attractive are not going to scale. As long as you work, and I've seen this happen so many times, people start out, you have to start working on simple problems, on simple missions. We're going to simulate simple training examples. And so we have this great approach that works really well on the simple example, and then we say, okay, let's soup it up. Let's make it more realistic, and the more we do that, the more we find finite state machines just aren't working anymore. Because they don't know why they're doing what they're doing is a big part of it, as I argue. Now, so the field of artificial intelligence tried to address this for a few decades by expanding the notion of state machines to the notion of search. Okay, I'm going to give you a very simple example of what that looked like. So this is a classic example that's been used in artificial intelligence research for 70 years, the blocks world. So the idea is you have a robot arm that's moving blocks on a table, okay? And you start with a particular configuration of blocks, and in this case, you have a goal. The goal is to build a tower of blocks where A is on B and B is on C, okay? But this is the state we're in. So this still has the idea of states, just like a finite state machine, but now there's this notion of search, which is I have certain actions I can take. I have a robot arm that can pick up blocks and put blocks down. So the question is, what sequence of actions should I take in order to achieve my goal? So in this case, I can take the block A off of B and put it on the table, and that moves me to a new state. So what we have here, we call this an operator. So the operator is something that changes my situation from one state to another. When I execute that operator, I'm now in a new state. Okay, so there's still this notion of states. Now I can stack B on C. I've applied another operator. I can stack A on B, and now I've achieved my goal. Okay, so this is similar to finite state machines in that there are states, but now there's this notion of operations I can take to move myself from one state to another. It's not just based on what's happening out in the real world. And there's this notion of search. To be smart, there's a whole space of things I could do, and being smart means I find the path, the sequence of operators to use that take me to my goal. There's all sorts of operators I could take that wouldn't get me closer to my goal. And so what an intelligent system is about is finding the sequence that gets you closer and closer to your goal. Okay, so this is a paradigm, the search paradigm drove a lot of AI research, but it still has some limitations. So it allows us to no longer have to do the linear flow of control that finite state machines impose on us. We can now we can jump from one state to another depending on the operators we use, or we can think about different states. We can think about multiple states at the same time. To some extent, it addresses, the search-based approach addresses these other things having to do with learning and having to do with understanding why I'm doing what I'm doing, but it's still the case that these search-based systems don't scale with complexity. And this is what we spent decades in the field of artificial intelligence learning hard lessons about. Lots of PhD dissertations were focused on how can we make this search paradigm work on more and more complex kinds of things like air combat. So let's ground this in example. Okay, so this is taken from a project that I worked on, which was to build synthetic aircraft that fly close air support missions. So the idea here was to train the terminal air controller. So terminal air controllers on the ground, they identify a target, they call in for a close air support mission. The pilot of the aircraft who's going to do the close air support mission checks in with the terminal air controller, and we tell them where the target is, when we want them to bomb the target. We tell them if there are any friendly forces nearby, and then the pilot goes in and bombs the target at the right time and from the right direction. Okay, so the idea is we want to automate that system that's flying the aircraft so that it can interact with a human terminal air controller and help them train. So first thing we did is we talked to human pilots and human terminal air controllers and talked about, okay, tell us how these missions proceed. How do they go? And we talked to instructors. It's very important to talk to instructors because instructors are not only experts in how to do the mission, they're also experts in how to think about doing the mission because they have to communicate how to think about things to their trainees. And that helps us build these cognitive systems because we get their knowledge representations from them and engineer them into the system. So the first thing they tell us is, well, there are these mission phases you go through. And you know what? It looks a lot like a finite state machine. So you think, okay, let's try that. You know, if there are these distinct mission phases, then maybe we would want to use a finite state machine to implement this pilot. Okay, so here's what looks like the state space for close air support. First, you do your takeoff procedures. You take off, you enter the area of operations, then you check in with the terminal air controller, and he's going to give you the target information and any constraints around the target. And then you have options. Sometimes you will hold until it's time to proceed to the target. Sometimes you will ingress immediately to the target, so you figure out which direction you're going to approach the target from and then fly over the target. Sometimes you're able, in some situations, you're able to do what's called an immediate attack. You don't need to follow any particular ingress route, you just fly to the target and deliver the ordnance to the target, okay? But if you do hold, then you'll go to an ingress and you'll go to an attack. So again, we've got a clean sequence of states here. Once you've done the attack, you can egress from the attack, and you might go back and do another attack, or you might go back and do another ingress, or you might go hold and wait to do another attack, or you might be done and you leave the area of operations and you go return to base and land, okay? So that looks a lot like a finite state machine, okay? So that's the first thing even the human experts tell you. These instructors say you, these are the phases of a close air support mission. These are all the different kinds of situations you might be in. And then you start giving them some scenarios and asking them, what are the different things you might do in each of these states? And you quickly learn that it's not really a finite state machine, especially if you're an expert pilot. Maybe novices would go through these mission phases very carefully because they don't completely know what they're doing, so they want to follow what they've been told. But expert pilots will tell you, well, you know what, sometimes I won't bother to, sometimes I'll proceed straight to the ingress while I'm checking in because I know where the target's going to be. So I don't need to check in first to find out where the target is. I can kill two birds with one stone. And it turns out in all these states, there's an ability to jump from one state to another. There's an ability to sometimes do the activities in two states at once. And the boundaries for these states aren't really hard and fast boundaries. You can consider yourself in some ways to be doing, to be in two states at the same time. So even when you're doing the attack, you might, or the ingress, you might ingress in a way that is influenced by how you want to egress, right? And so you're thinking about the egress while you're doing the ingress, and so it's just not as tidy as you might have hoped if it was going to be a finite state machine. So, and the reason the expert pilots are able to do these kinds of things is because they understand why they're doing what they're doing. When they're checking in, they know the ultimate goal is going to be to deliver ordnance on a target. That's why they're checking in, okay? So that influences how they can check in, right? They know that I need to check in, I need to get information that the terminal air controller has. Maybe I don't need that information. Maybe I've already been pre-briefed with all the information he's going to give me, and I just need to check in and tell him I'm here. All these different exceptions make it so that I can focus my attention on what the real goals are, and because I know why I'm doing what I'm doing, I can violate the boundaries of this finite state machine. So how would we really represent cognitive close air support if we were building a software system to do this? Well, we actually built such a system. So we defined a bunch of different types of goals. First, there's categories of goals. There's goals to survive. There's goals about how to maneuver the aircraft. There are goals about what kind of communication do I need to do with the terminal air controller and maybe with other people. There is the actual mission goals, the close air support goals. There are goals in terms of the flight plan. Do I need to be at particular places at particular times? How do I manage my fuel? Things like that. So there are all these different goals that shape what the expert close air support pilot will do. And then in each of these category of goals, there are specific types of goals. So under maneuvering, there are speed goals, heading goals, altitude goals. Under close air support, there's a check-in goal. There's what tactics am I going to use for the attack, and so on and so forth. So there's all sorts of goals that the system is reasoning about, and then there's all sorts of things we call beliefs, which is our current situation understanding. So I know where there are or might be SAM sites. I know where there might be air threats. I know what my call sign is. I know that I'm flying with a group of teammates who are going to be performing the mission with me. There's all sorts of different information that makes up the situation. And I need to have an internal representation of what my mission situation is so that I can combine that with my goals. And as my situation changes, that might change how I'm going to approach my goals or even what some of my goals are. So this example is supposed to get you a flavor of what kinds of complexities we have. So if we think again about AI being search or state-based, the problem is that our states are not simple. Our states contain multiple types of information, multiple layers of information. There's beliefs and everything that makes up what my current situation understanding is. What are my current goals? What do I know about what's out there? What are my assumptions about what's up there? How am I interpreting what the terminal air controller is saying? How am I interpreting the actions of potential threats that are out there? All of these things go into what makes up the state. So the state itself is incredibly complex. If we were going to have a real finite state machine, we would end up with this combinational explosion of millions of states, and that would not be manageable. So we need a different approach. It's also the case that, in a sense, states consist of many states. So we have the state of our aircraft, we have the state of our mission, we have the state of our weapons. There's all sorts of different states that we would need to do different things about that combine into making what is the state of things that I need to care about when I'm making expert decisions. These states are also codependent, right? So a simple example is, on a fixed-wing aircraft, the radar points out the nose, right? So if I have sensing goals about which area of the sky do I want my radar pointing at, but I also have maneuver goals like I need to get to this waypoint, those goals interact with each other, right? They're codependent. I have to come up with actions that allow me to achieve all my goals at the same time. And add into that fuel goals, add into that weapons management goals. All of these goals impose constraints on how I can achieve my other goals. Experts know how to reason about those trade-offs, and we need to get that reasoning into the cognitive systems as well. Also, states change for many reasons. States don't just change because I took an action. States change sometimes because an opponent took an action, or a teammate took an action, or a system malfunctioned, or a weather front moved in. There's all sorts of things. So we can't just use this simple search-based approach where we have these things called operators that take us from one state to another state, because there's just so many different operators out there. So the idea is we keep the general notion of searches and states and operators, but we change how we represent things. So reasoning is now deliberative action on a knowledge representation. This is all centered on knowledge representation. How do we represent this complicated state that we're in? That's situational understanding. How do I represent in a computer model all the thousands of things that are relevant to the decision making I need to make? Operators are going to be the things that we do to try to change the state of the world. It can be as simple as turning my aircraft. It could be dropping a weapon, but there can also be internal operators. So when I decide, oh, there's a new goal I need to be achieving, that's an operator. An operator can change my mental state as well as the external state. And these operators are employed by what we call associative pattern matches. So it's no longer the case that we have these transitions. If I'm in this state, I transition to this state. Okay, that's what an operator used to be. Now, an operator is something that it can apply to any state. It has these associations. If this pattern of things is true, then I want to take this action. And this action can be an update to my situation understanding. It can be an update to what my goals are. It can be an update to how I'm trying to achieve those goals. Operators can do all these different things. So essentially, reasoning is recognition-based. We're constantly looking through, in a sense, our knowledge base to find out what knowledge patterns do I have that are relevant to my current understanding of the world. And every pattern that is relevant to my current understanding of the world is then allowed to make changes to my current understanding of the world, in which case now new patterns. You can think of this sort of as neural networks, right? I mean, I'm not talking about machine neural networks, I'm talking about human neural networks. We have these circuits of neurons that, you know, it's rarely the case that just one neuron fires at a time. They usually fire in bunches, and we call that a neural circuit. And what they're doing is they're recognizing a pattern. When I'm looking at a room full of people, there's certain neural circuits that are firing, saying, hey, you're looking at a room full of people. And then if I look at a particular face, I'm going to have neural circuits firing that are relevant to the features of a person's face. That's the same kind of thing that's going on here, except obviously we're not using neural circuits, we're using computational pattern matching technology, and there's very, very efficient algorithms for doing that, allowing us just to match a pattern to an action, match a pattern to an action. And that's the basis of the engineering of these cognitive systems. This also allows operators to interleave their actions because it's no longer sequential. You know, any knowledge pattern that is firing says, hey, I'm ready to fire, you should pay attention to me, and we execute what that knowledge pattern says to do, and then another pattern can jump in, and I'll give you an example of that. But that gives us what we call least commitment reasoning, which I'm setting aside as its own topic here because I think it's central to how cognitive systems operate that is different from how your traditional software engineering systems operate. So again, least commitment reasoning is also sometimes called satisficing. Basically, make the best manageable decision in a very short amount of time. And the more expert a human is, the faster they can do that, and the better the resulting decision is, okay? And this is an iterative process, so experts are constantly doing this. As the situation is unfolding, they're constantly reassessing what's going on, what should I be doing about it? What's going on, what should I be doing about it? And this allows you to compose innovative solutions to problems because different neural circuits relevant to different parts of the problem can combine to contribute their inputs to what your goals should be and how you should be trying to achieve those goals. I'm going to skip this slide in the interest of time. I have often talked about rule-based systems because they got a bad rap way back in the 70s, but I'm not so sure people care that much about it anymore. But I want to get to my example. So just to explain how least commitment works. So the idea is, say we have two robots. What I would call a high commitment robot is one that has a script. It has a specific plan to follow. But if it loses its place, it's lost. It doesn't know what to do. Where a least commitment robot has no script, but it always is engaging in this understanding and recognizing what it should do next. Now, so here's my example. Okay, so question time again. How many of you have cookbooks at home? Okay. Some of those cookbooks are written by expert cooks, I imagine. All right, okay, put your hand up again if you have cookbooks written by expert cooks. Okay, now, keep your hand up if you are an expert cook. Well, okay, what's going on? You have a cookbook written by an expert. You have all the knowledge you need right there, right? So why are you not an expert cook, right? Well, I'm going to argue it's because you're a high commitment robot. You're not a least commitment robot. And that's partly because of the way the cookbook is written. Cookbooks give you recipes. And even though your cookbooks were written by expert cooks, they weren't necessarily written by expert cognitive scientists. who are experts in training and education. There is a way you would write the cookbook if you were a cognitive scientist that would be different from being an expert at cook. So let's look at an example restaurant. So let's say you have a cookbook with a recipe for making pasta and cheese sauce. Okay, now I've written this in a stylized way. It's sort of like what you would actually see in a cookbook, only I made it look more like a computer program. Okay, so it's a bunch of numbered steps. So to make pasta and cheese sauce, I'm first gonna fill a pot that I'm calling pot 1 with water. I'm gonna heat pot 1 until the water boils, add pasta to pot 1, stir it until it's soft, drain the pasta, and then I have another pot. I'm gonna put butter in. Basically, I'm making a roux here to make the cheese sauce. Okay, put butter in it, butter melts, add flour, mix the flour into the butter, add milk, let it thicken, add the cheese, and then I'm gonna mix my cheese sauce and my pasta, okay? So that is a high commitment version of a recipe for pasta and cheese sauce. Okay, one thing to notice here is there's some idiosyncratic things, like I have you boil the pasta before I have you make the cheese sauce, right? Well, why not do them both at the same time, right? Maybe a cookbook would tell you that, oh, you can do these things both at the same time. But the very nature of a cookbook is it's sequential, right? It's written words on a page. That's the same thing of standard software engineering systems. They're inherently sequential. I mean, there are now multi-threaded systems where you can do 2 things at once. So yeah, you can do that kind of thing, but they're inherently sequential, and it's up to you to program it if you wanted to do 2 things at the same time. It's not up to the system to decide for itself, oh, hey, I could do these things at the same time. So let's look at what a pasta and cheese sauce recipe might look like if it was a least commitment recipe. Okay, I'm gonna start by, I'm gonna have the exact same instructions I had before, except I'm gonna put an if statement at the beginning of every one, which is basically gonna tell the system, why are you doing this step, okay? So I used to have fill pot 1 with water. Now I'm saying, if pot 1 is empty and the pasta is uncooked, fill pot 1 with water. If pot 1 contains water and the pasta is uncooked, heat the water in pot 1, okay? I'm doing this with every line. So this is the exact same actions I had in the previous recipe, but every line now has conditions on it saying, here's when you should apply this action, okay? First thing this means is I can get rid of the line numbers, okay? Because the line numbers were just there because it was in a book and it had to be in order, but I don't need the line numbers anymore. So now, if pot 1 is empty and pasta is uncooked, I can fill the pot 1 with water, but if pot 2 is empty and the sauce is not done, I can put butter in pot 2. There's nothing telling me that I can't do those both things at the same time. There's nothing ordering those steps for me anymore. So a smart cognitive system can look at this and say, oh, okay, I've got 2 things. I can do them both right now. I can choose. I can do one first and then the other. I can do them both at the same time. Another thing is, well, what if someone, maybe a partner robot, already gave me a pot of cooked pasta? So I don't need to do that part. Okay, well, so I'm not going to do any of these first steps. Pasta is uncooked, pasta is uncooked, pasta. Well, no, I have cooked pasta, so I don't have to do those 3 steps. I can take advantage of this opportunity. If I boil my pasta and then someone knocks it on the floor, I'll do it again. All right, there's nothing in here that says, yeah, so now I no longer have now pot 1 is empty again, right? So now I'll just go back and do that again. So you can interrupt me, you can mess with me. As long as I've got my knowledge patterns represented correctly, I can recover, right? So the more expert I am, the better patterns I have, the better I am at taking advantage of opportunities, handling interruptions, doing 2 things at once, all the things that human experts are good at, okay? So this is how we engineer the knowledge representation inside a cognitive system. And that's maybe the key takeaway I want you to take from this tutorial, is you can build systems like this. It's different from how we usually build software systems, but the point is you have some work to do. You need to find out for every action you can take, why are you taking that action, and engineer that into the system. Once you do, you have a robust, intelligent system. Okay? I just want to add, this isn't a complete recipe. When we really build these systems, we actually add a little more to the if statements because we also have this notion of goals. So if I were really building the system, I would have things like, well, if my goal is to make pasta and cheese sauce, then create a sub-goal to have cooked pasta and a sub-goal to have cheese sauce. And if my goal is to have cooked pasta, then create a sub-goal to have a pot filled with hot water. So we actually build into the system this knowledge for deciding what my goals should be, how I can decompose goals into sub-goals. And again, these goals and sub-goals can be fluid. They can change if my situation changes. So that's just to give a flavor of, these systems are a little bit even more complex than what I hinted at with my pasta and cheese sauce example. So what are the advantages to this least commitment design? Any or all of the actions can be executed or omitted based entirely on the situation. Okay? Situation changes, then different patterns light up, and I execute different actions. The model will smoothly handle interruption, task switching, opportunities, achievement of goals. You can work together in teams where multiple robots are working on the task, and if someone else does something, then I don't have to do it. Unexpected world changes we handle. Parallelism is constrained only by how I think about the task. It's not constrained by having line numbers on the recipe. Okay? So if my knowledge is expressed in a flexible enough way, then my cognitive system can be very flexible in how it applies that knowledge. There's an underlying system called a cognitive architecture that provides the machinery to manage all this. So if you, I don't know how technical to get in terms of software engineering, but if you program in Java, for example, there's something called the Java virtual machine. Okay, the Java virtual machine is a layer of abstraction that allows you to write programs in Java that will execute on Windows and execute on Apple. It will execute on Android, right? So there's this abstract machine we call a virtual machine that can then run on all these other kinds of machines. Well, cognitive architectures are a layer above that. You can think of a cognitive architecture as a virtual machine for cognition. So cognitive architectures are software systems that give you methods for managing your memory, managing your pattern matching, managing your representation of goals and situation understanding. There are a few different cognitive architectures out there, but the point is there's already software infrastructure out there to allow you to build these kinds of systems. Now, the downside is there are not lots of software engineers who know how to build these systems, right? That is something that will only happen over time and with experience. But the basic idea, the way these cognitive architectures work, is they have a loop. And they execute this loop possibly millions of times per second. It's similar to a loop that's going on in your neural circuits. You sense the environment. Basically, there's some input, some stimulus out there that gets fed into the system. Based on that, you revise what we call your beliefs. Basically, you update your understanding of what the world is. Based on your new understanding of the world, you revise what we call your desires. Your desires are what we call the things that you wish were true, okay? And then you revise your active goals. Active goals are the subset of desires that you have decided, I'm going to commit my cognitive resources to trying to achieve these goals. So there are things you might wish would be true, but you're not going to spend your energy on right now, okay? Only the things you're spending your energy on right now are what we call the active goals. Then you consider plans for achieving your set of goals. You might have lots of goals that are active at the same time, and then you execute the next action in your plan. And possibly that means you're issuing motor commands. If you're a robot, maybe you're issuing the command to pour water in the pot, right? and then there's a loop. So this is a very reactive system. Again, cognitive architectures give you very efficient virtual machines for implementing this cycle, where it's just constantly sense the environment, update my beliefs, update my goals, take an action, and then do it again. And again, on modern hardware, depending on how complex the problem is, you can be doing that thousands or millions of times per second. Roughly, the estimate of how the human brain does this cycle is maybe once every 50 milliseconds, 50 to 200 milliseconds. And so modern computer hardware can be faster than humans, but it's also not quite as sophisticated in terms of the knowledge it has as the humans are. Now, in terms of the beliefs, this just gets a little bit into details. There's different kinds of beliefs that cognitive architectures support. One is called an entailment. So a logical entailment is a belief that's grounded in something you're perceiving right now. So like right now I'm holding up this pen. The fact that you can see this pen, it's stimulating your neural circuits right now. There's a physical thing going on, feeding in. That is a logically entailed belief that I am holding a pen. It's justified by what your perception is telling you. Now, if I have an assumption is a belief that you don't have direct support for. So like, am I still holding the pen, right? You might think, okay, yeah, he's probably still holding the pen because he was just holding it. He just moved his hand down. But until I hold up my hand and you see that I'm not holding the pen, now you've got a logically entailed belief that violates the assumption, so you're more likely probably to believe the logically entailed belief. But the point is that assumptions are important. You need to have assumptions as part of your situational understanding as well. And then there's also associations. You might have, the fact that I'm holding a pen, maybe that means I'm going to write something, maybe it means I'm going to point at something. These are things that might contribute to your situational understanding. What are the relevant reasons he might be holding that pen? Okay, so there's all these different kinds of things that go into beliefs, and the main point I'm trying to make here is that cognitive architectures provide mechanisms for representing these different kinds of beliefs, these different ways of representing situation understanding. They have different ways of representing goals also. And the thing about goals are a big part of the why, okay? A goal tells you what the system's trying to achieve, but that's also a why for any action the system might take. So if you want to ask, well, why did you do that? It will say, because I was trying to achieve this goal and because I had these beliefs. So the very fact that we're representing beliefs and goals are what are giving this cognitive system this ability to justify what it's doing or support what it's doing with these whys. So that's the sense in which I say it's not a cognitive system unless you've incorporated these representations of knowledge so that the system knows why it's doing what it's doing. So I want to give another example from a system we built. So this was an air-to-air combat synthetic pilot for training simulations. And this might be kind of an old-fashioned example now. We built this system originally in the 90s. But the idea here is that the blue aircraft has come in to intercept a red target, fired a missile at the red target, and then the blue aircraft offsets its nose by, say, 30, 40 degrees. So you could ask the system, well, why did you do that? Why did you turn right after you fired that missile? Some of you might know the answer, and I'll tell you the answer. But first, let's consider, well, how would you answer that? So if you had built the system as a finite state machine, in a sense, it could only give one answer. It would say, well, I was in the state where I fired the missile, and that took me to a new state, and in the new state, it told me to turn right 40 degrees, and so that's why I did it. That's not a very trust-inspiring answer, right? It's not very informative. It doesn't make me think, oh, this is going to be a great teammate. He really knows what he's doing, right? But a cognitive system would be able to give a better answer to that. Just as an aside, if you asked a generative learning system, like a large language model, if you asked ChatGPT, why did that aircraft turn right, it would very confidently give you an answer, and it might even be the right answer, but it could just as confidently be the wrong answer. It would string something together based on information it's collated from the web. But the cognitive system knows why it did it. It did it because this was a semi-active radar-guided missile. Semi-active radar-guided missiles, at the beginning of their flight path, are guided by the radar on the aircraft that fired the missile. And so the aircraft that fired the missile must keep the target on its radar in order for that missile to keep guiding at the target. It's not until the missile gets closer to the target that it takes over and uses its own radar. So you could say, well, why don't you just point straight at the target? Okay, well, you could do that because that way you're keeping the target on your radar. But if the target's shooting at you and you point at it, you are giving it a really fast approach to its missile. And so if you turn just so the guy's on the edge of your radar, you're able to guide your missile into it, but you're also making it so that anything they shot at you is going to take longer to hit you. And hopefully your missile hits first. But that's why. That's a standard tactic called a crank maneuver. Expert pilots know to do that. Novice pilots don't know to do that, and that's what I've been told has given American pilots advantages in many engagements over the decades. So you're not meant to be able to read this, but each of the dashed lines in this picture is taken from an actual system we built called TAC-AIR-SOAR that provides synthetic combat pilots for training simulations. And each of those dashed lines is one of those pattern matchers that builds the situational understanding representation. So this has all the information about the limits of my radar. My radar can sway 60 degrees. I have a missile that's of a semi-active type. It needs to be supported until it's so far away from the target. The reason I'm doing all of this is because I identified that target as hostile and I was ordered to kill the target. All of that's in here. And so if you ask this, you can ask the system, why did you turn right? And it can say, well, I wanted to slow down the approach of an enemy missile while also guiding my missile into the target. And you could say, well, why did you fire the missile? Oh, because it was identified as a hostile target and I was within the intercept range of the target for this missile. All of that information's in here, so in theory, you could ask any of those questions and it will be able to tell you the answer to that question, again, because the system has in its knowledge base why it made each of those decisions, because each of those decisions was a complicated if-then statement, just like the pasta and cheese sauce example. Whoops. So I want to finish here with, I'm going to go a little bit over because I have to talk about learning too. So I promised you I would give you some decision-making principles for when should I be using a cognitive system. If I want to build a simulation or an automation system or a training system, should I use finite state machines? Maybe my problem's simple enough that finite state machines would be a better approach. And sure, that might be right. But I want to tell you the questions you can ask to decide, well, maybe I should consider hiring someone who knows how to build cognitive systems. So first, and we ask these questions of ourselves. Before we write a proposal for a new project, we ask these 5 questions, and if we can answer 3 or more of them as yes, then we say, yes, we should use a cognitive system for this. That's just our rule of thumb. So does the application require attention to parallel tasks that are sensitive to each other? So it's not just that you're doing 2 things at once, but the way you do those 2 things have an influence on each other. If they were just independent of each other, you could just use multi-threaded programming and it wouldn't really be a problem. So, but this means you your actions have a dependence on your common understanding of everything that's going on. You're Wayne Gretzky. You know everything that's going on out there, and you're trying to do multiple things at once. Does the application require handling large numbers of special cases and exceptions? Something human experts are very good at. If there are no special cases or exceptions, you can just write a general algorithm that will always work, right? But it's when the devil's in the details that you need some expertise to handle all these weird, strange things that can happen. Does the application require quick, dynamic, and robust adaptation to changing situations? So do you need to be able to change your goals quickly, change your understanding quickly, change how you're achieving your goals very quickly because lots of complex things are changing? If so, then that's a point in favor of using a cognitive system, because I'm going to argue you really need to be using a pattern recognition-based system instead of a linear flow of control, which you get in a standard software engineering system. Does the application require flexible interruptibility and opportunism? These are the kinds of things we looked at in the pasta and cheese sauce example. Can you lose your place and come back and finish what you were doing, or take advantage of something that has happened in the world and kill two birds with one stone? And does the application require natural collaboration with human users, right? So if you are going to be a teammate with a human, we as humans generally expect our teammates to be able to explain to us why they're doing what they're doing, so that we can make sure we're on the same page, achieving the same goals, achieving the goals in a way we agree on. So that has to be represented somewhere in the system you're working with if you're going to treat them as the same kind of human teammate that you would treat a human teammate. Okay, let's finish by talking a little bit about learning. I probably have too much here. So I added this to the tutorial because learning is everywhere now, and it's wildly successful. Okay, so machine learning is not part of this tutorial because there's enough in this tutorial already. Machine learning could be its own tutorial, and in fact, I'll be giving a machine learning tutorial in the next session. Okay, it's a very high level, it's called Machine Learning for Humans. Doesn't get into technical detail at all. It's just kind of, what is this stuff, and a very high level, how does it work? But the other tutorials around this one in this session are more in detail about certain kinds of machine learning. So there's lots to say about machine learning, but the upshot is building this kind of cognitive system I talked about can be expensive. Someone has to engineer all that expertise from the human expert and build it into a system. But learning is also expensive. It's just the expense is somewhere else. You don't have to manually build the system and build the knowledge, but you have to train your learning system sometimes on billions or trillions of training episodes. So, I mean, there's a lot of work that goes into building these learning systems as well. So there's a trade-off. What do you need it to do, and where do you want the expense to be? There's also the fact that humans can still learn some things that even the best machine learning systems can't. If you want more answers on that, come to my next tutorial. But there are certain kinds of learning machine learning is really good at, but there's still some things humans do well that machine learning systems don't. So we still want to ask questions if we want to integrate learning into our cognitive systems, which obviously I think we want to do. We want to think about what, why, and when should my application learn. We provided a framework for all the different places you might introduce learning. So we've talked about beliefs, desires, goals, situation understanding, interleaving, all of these decision points. Any time the system takes action, there's an opportunity there to bring learning into the system. Of course, the devil's in the details, right? How do we integrate these really good learning algorithms with these really good reasoning systems? And that is an area of active research. So I would suggest the path forward, the best learning algorithms are flexible, fluent, and tolerant of what we call noise. That is, they can handle learning things even when there's mistakes in the training material. but they're really good, but they're opaque. They can't really right now tell you why they're doing what they're doing. So dogs are very good learners too, but if we want human teammates and human-like teammates, in the long run, we want things that are really good at learning, but really good at understanding, and really good at communicating and explaining why they're doing what they're doing. Maybe learning systems will be able to do that all on their own some days, but I think it's more likely that it'll be an integration of these knowledge-based cognitive systems and these data-driven learning systems. In addition to being good learners, humans can communicate what they know, explain themselves, collaborate, all things that are so far weaknesses in the machine learning systems. So I would argue the most robust future learning systems will also be cognitive systems, and the best future cognitive systems will also be learning systems, and we are still actively figuring out how to make both those things come true. I'm going to skip this because I want time for questions. So take-home messages, you need cognitive systems. If we're going to have human teammates who are cognitive force multipliers, they need to understand why they're doing what they're doing. There are currently a variety of cognitive systems out there. The good ones have adaptive, complex behavior, and they do understand why they're doing what they're doing. And I've given you at least a few questions you can ask to decide for yourself, should I consider a cognitive systems approach to my problem, or should I consider some other approach? Those are our learning objectives, and I will open for questions. Thank you. Yes?
How do you deal with conflicting goals in the cognitive system?
How do you deal with conflicting goals? So it's, there are different mechanisms. There are what we'd call domain general and domain specific mechanisms. So some kinds of conflicts are they're pretty general. Like if you wanted to, I don't know, chew gum and walk at the same time, right? There's only a conflict there in terms of your cognitive pipeline. It's not. It's just for some reason they're hard to do, and we don't know why. But often it's an expert level thing. So it's very domain specific. So example of the one I gave you of where we need to, we want to, when we fire the missile, the best thing we'd want to do is just run away, right? Because we don't want them to shoot us. But we can't do that because we have to support our missile. So there's two conflicting goals. So how do we do that? Well, in this case, it's sort of an optimization problem. Let me decrease the risk of getting shot down as much as I can while I'm maintaining the capability for my missile to hit the target. But this is often a thing we would just ask the experts, right? So that's something, again, a novice doesn't know to do that. An expert does. And so one way we handle this is handle such conflicts as we ask the experts. What do you do when these goals conflict? But another way would be to have sort of a background reasoning system, sort of a default reasoning system that kicks in when we don't have the expertise. If I have two goals that try to use the same resource, in this case, the direction of the aircraft, in ways that conflict with each other, then maybe I can build in some default knowledge for, well, split it down the middle, something like that. There's different approaches you can use. Yes?
Pragmatically, how are cognitive systems built with current technologies? Is this something that you are going to code by hand in Java or C++? Is it going to involve some machine learning? Like, what does it practically look like?
What, I didn't hear all of that, so I can get.
Sure. What will it look like to practically build a current state-of-the-art cognitive system? Do you do that with manual programming by hand? Do you use machine learning? Are there models involved? If I was going to start to build one of these things, what would I?
Right. So how do you practically do these things? I mean, from a practical perspective, it's a software design problem. It's a complex software system, and we've used all sorts of different approaches. We have, for these cognitive systems, we have integrated them some with learning, but we're only beginning with that. We don't really have that solved yet. So most of the cognitive systems we've built have been built by hand, and so it's like building Microsoft Word, right? It's like it's just a really big software system, but we have lots of design patterns and knowledge representation patterns that we reuse, and that helps us make it not a totally intractable problem, right? And we have this approach of, you identify the goals, you identify the language for the beliefs, and then you determine what the choices are, what the reasons are for deciding between different choices. So it's a combination of, in a sense, it's a requirements thing where the requirement is match the human expert, right? And then there's the engineering. And I would say the requirements is 80% of the work, right? It's finding out, how does the expert really think about this? Now, once you've got that, I can see lots of opportunities for introducing learning to some of those, and that's part of what I had in this slide, but we're still working on how to do that best. One of the things I think is most promising probably is, even after you've engineered as much knowledge as you can get from an expert, there's going to be gaps where the system doesn't know what to do, right? Well, at that point, you have these encyclopedias basically now of ChatGPT. You can say, here's the problem I'm facing. What do you think I should do? I think that could be fruitful, even though, again, it's not always going to be a great answer, but it's probably better than nothing.
Would you also use a cognitive system to manage entire teams, like the entire hockey team, instead of just
We have done it for teams too. Basically, this isn't the only approach you can use, but the approach we use is we try to create a cognitive system so that it's a drop-in replacement for a human. So if you have a team, so basically what that means is it tries to use the same language, the same goals, and the same verbalizations as the teammates use. So that if you have, say, 4 humans flying a 4-ship air combat formation, you can replace one of those humans with a cognitive system and everything still works. Or you can replace all 4, and the way they collaborate with each other is the same way the humans. So they send natural language radio messages to each other and things like that. But yeah, there's lots of work on teamwork in artificial intelligence, and some of it's very theoretical. I would say a lot of it is very theoretical, and ours is, I would say, more, our approach uses some of the theory, but it's more based on the pragmatics, again, of we're trying to replicate humans here. So we ask the humans, how do you cooperate with each other? How do you coordinate your actions with each other? And they tell us, and we engineer that into the system. But yes, we do group behaviors as well as individual behaviors. Yes.
So then, with the hybrid models, more linear, deterministic style visual state models. So on that side, then, the least commitment models could be why and the if, in that sense, be justified by prior probabilities, such as if you use like a hidden Markov model or something along those states, where you're learning, so you're asking, why would you possibly do this?
Yeah. Yes, you can absolutely do that. And we build systems like that to basically to debug our systems, saying, okay, if this were true, what would you do and why? And also we have interfaces. We say, explain yourself. Why are you doing this? And if it tells us a reason that we don't like, then we know there's a bug in the code, right? But yes, you can do hypothetical reasoning by, we basically have these things we call the hallucination machine. We say, okay, pretend you're in this situation, what would you do and why? So yeah, yes.
I asked ChatGPT, an aircraft fires a missile on an enemy aircraft, then turns 40 degrees to the right. Why did it do that? When an aircraft fires a missile at an enemy aircraft, then turns 40 degrees to the right, it is likely employing a crank maneuver or a related defensive tactic. And then maximizing closure rate, reducing vulnerability to retaliation, including beam threat, diminishing radar cross-section, maintaining situation awareness, and evasive preparations.
That's great. So that's a good answer. And to me, that raises an interesting question because ChatGPT probably can't fly air combat missions, but it can provide a good explanation for why a system that can fly air combat missions does what it does. And you know, there are philosophical questions about, you know, whether we do the same thing. When we're explaining what we're doing, are we just explaining what we think we were doing, or are we actually explaining what we were doing? Yeah.
So basically, you use your data set from scratch, or you use some sort of large language model?
I'm afraid, can you repeat the question?
Did you build your data model from scratch or use a large language model?
The data model.
What?
How did you build your data model?
For your scenario.
I want to be clear. What do you mean by the data model? Do you mean our knowledge representation model, or?
That's right, yes, because you're going to need data to train your system, right?
So
Data from
these aren't what I've talked about aren't learning systems. So we're not training the system. So we are handcrafting the knowledge representation, which in a sense so it's similar to the data model problem. You know, when you're training systems, you have to decide how you're going to structure the data you feed into the system and how you're going to structure the output. And again, we base it on the expertise we're getting from the human experts, as well as often we're working in simulation. So what does the simulation system provide? So we marry those two things together to decide, you know, what information is relevant to decision making, and how can we compute that information from the simulation.
Unfortunately, we're out of time, but I'm sure Randy will be willing to hang out for a few minutes.
Sure.
Please drop off your feedback form with Ramona in the back. And if you can, join us at 12:45, where Dr. Ramona Shires is going to be presenting on generative AI. Thanks, Randy, for your talk.
Thank you so much.